Hey guys, how's it going? In this video we're going to look at our fourth and final application of fields, which is the charge to mass ratio for electrons. So let's get going. Now we're going to look at the classic experiment for determining the charge to mass ratio for electrons, and this method uses the idea of crossed electric and magnetic fields mentioned above. Now the sketch of the apparatus here shows you've got a heater with a cathode and anode, where the cathode produces the electrons and then between the cathode and anode the electrons are accelerated. We've then got some Helmholtz coils set up parallel to each other with the screen in between them. And you can see what happens when you've got a magnetic field only, where the electrons would enter here with a velocity v, but they travel in a curved path with a deflection y. And in this case we have plates of a length L. It firstly says the electric field E is applied by the potential difference V across the plates. So that's at the plates between the cathode and anode. The separation of the plates is d and their length is L. The current in the Helmholtz coils is slowly increased until the opposite magnetic deflection cancels out the electric deflection and the electron beam appears undeflected. And then using the magnetic field only, the deflection of the beam y is noted. For the undeflected beam, we could write that the magnetic force is equal to the electric force, just like we did for the velocity selector and mass spectrometer. So that gives us QVB is equal to QE, and as before, the charge Q on both sides will cancel out, so we end up with VB equals E, or rearranging for V, we get V equals E over B. And that was the equation for velocity for the velocity selector. And lastly, we can say that for the magnetic field only, the centripetal force is provided by the magnetic field. So the particles will be deflected, they'll move in a curved path due to the magnetic field, and therefore we can equate the magnetic force to the centripetal force. So we have QVB equals mv squared over r, and then dividing both sides by VB and m, then we get Q over m on this side is equal to V squared over V times RB, but then we'll have a V squared term on the top and a V on the bottom, so that V squared will just become V on the top and it cancels out the V on the bottom. So we end up with an equation for charge to mass ratio for electrons, which is Q over m equals V over RB. So you can see it depends on the velocity of the electrons, the radius of curvature, and the strength of the magnetic field, i.e. the magnetic induction B. Now I'm just going to show you a quick simulation to help you visualize this. So here's a picture of our screen where we'll get a circular beam for our electrons shown. And the table of data shows the voltage in volts, the velocity of the electrons in meters per second, the coil current in amps, and the magnetic induction or magnetic field strength in Tesla. And we've also got a radius in centimeters. And you can use these to work out the charge to mass ratio in this experiment using the equation E or Q over m equals 2 times the voltage divided by B times R all squared. And that's in units of coulombs per kilogram. So I'll show you just one example of these, and let's just use the maximum voltage here and the maximum magnetic induction. And you can see we've got our circular electron beam on the screen. So I'm just going to write in 300 volts for our voltage, and this spits out our velocity here as well, 1.027 times 10 to the 7 meters per second, and I'll put in our current of 2.50 amps as well. And you can see this also gives us our magnetic induction in Tesla, so 1.87 times 10 to the minus 3 Tesla. What we can then do is use a guideline to measure this radius, so if we get our circle sort of just overlapping that one there, just about, we have a radius of roughly 3.05 centimeters. So I'm going to write that in here, 3.05, and then it's spitting out my answer of charge to mass ratio. So we've got 1.84 times 10 to the 11 coulombs per kilogram. And what you would want to do here is get a range of different values of voltage and current by changing the electric and magnetic field strength. But with this value, 1.84 times 10 to the 11 coulombs per kilogram, let's see how close that is to the expected value. So if we look here, we've got some sample data, and they're saying that the accepted value from the literature is E over m equals 1.75882 times 10 to the 11 coulombs per kilogram. So about 1.76 times 10 to the 11. So our 1.84 times 10 to the 11 is not too far off. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.